Hey chemistry! So today we are going to go over the combined gas law and Avogadro's principle. Yes, the avocado guy that we learned about, he's got that number 6.33 times 10 to the 20. Yeah, you know the deal with all the moles, the number of particles in a mole. Today we are going to carry on with some of our gas laws, and we're going to learn about the combined gas law. So we talked about Charles' law and Boyle's law, and they really only deal with two variables at a time. But what happens if you're dealing with more variables than that? Let's talk about it. So the combined gas law states the relationship between pressure, volume, and temperature of a fixed amount of gas. So you have a fixed amount of it, but it can expand in volume, yada yada. But the number of moles, like the number of particles in there, isn't going to change. But the equation can be expressed as such. So you have P1 V1 over T1 equals P2 V2 over T2. So the biggest thing is you need several of these. You really can only solve this with one variable at a time. So for example, if but the thing is you can ultimately create this out of Charles' law, Boyle's law, Gay-Lussac's law. So this is only if you've got different things changing and different conditions where you have more than two things changing. So let's read an example where you would figure this out. Okay, so this is the example problem on page 429. Now, if you have a gas at 110 kilopascals at 30 degrees Celsius and it fills a flexible container with an initial volume of 2 liters, if the temperature is raised to 80 degrees Celsius and the pressure is increased to 440 kilopascals, well, what is the new volume? So why do we need the combined gas law? Why couldn't we just use something about pressure and volume? Well, because both pressure and temperature are changing. And when you have more than two things changing, we're having pressure, temperature, and now we need to find a new volume. So when you have all of these three things changing, you now need to figure out an equation that's going to relate to all three of those differences, okay? So let's write down what we know from the problem. We know the initial pressure is going to be 110 kilopascals. We also know the initial temperature is going to be 30 degrees Celsius. But remember, we always have to use Kelvin, so let's convert it to Kelvin. Plus 273 equals 303 Kelvin. And our initial volume is given to us, fills with initial volume of 2 liters. Now, let's read about where it goes. If the temperature is raised to 80 degrees Celsius, so temperature 2 equals 80 degrees Celsius. But remember, we have to do Kelvin, so plus 273. Sorry, not plus, equals 553 or 353 Kelvin. And the pressure is increased to 440 kilopascals. So pressure 2 is going to be 440 kPa. Double check, make sure both the pressures are in the same unit. They are, so we can go forth and solve it. So we adjusted our temperatures to be Kelvin already. Now, all we do is we plug it in. All right? So we've got pressure 1, 110, times volume 1, 2, divided by temperature 1, 303, equals pressure 2, which is 440, times volume 2, which we don't know, that's our unknown, divided by temperature 2, which is 353. So now, I need my calculator, let's break it down. We can solve this whole first one all together. So we have 110 times 2. That's 220. 220 divided by 303 is 0.726 equals 440 V2 over 353. Well, let's get this 353 off the bottom, okay? So multiplied by 353 cancels that out. Multiplied by 353. We end up with 256.3 equals 440 V2. Now we just need to divide. Divided by 440, divided by 440. And we end up with 0.58. Let's look at our units. Liters equals volume 2. Now, that makes sense because the pressure's gone up a lot, okay? And so it makes sense that our volume would have to go down in order for the pressure to go up that much. All right? So that's an example on how to use the combined gas law, and those are the first couple problems in your unit 5. Now let's talk about Avogadro's principle. hopefully you remember him. He was the one who figured out, the number of atoms in a mole. Okay, I will erase this because we are going to talk about other things that take up space. Okay, so the particles that make up different gases can vary in size, right? But according to kinetic molecular theory, the particles in a gas sample are usually far enough apart that size has negligible influence on the volume. But, for example, 1,000 relatively large krypton gas particles could occupy the same volume as 1,000 helium gas particles, which are a lot smaller. And it was Avogadro that first proposed that idea. Today, it's known as Avogadro's principle. So the equal volume of gases at the same temperature and pressure can contain an equal number of particles. Why do we care? Let's get to that. Remember from chapter 11 that the most convenient unit for counting number of atoms is the mole, right? Because 6.02 times 10 to the 23rd, that's the number I couldn't think of. Because 1 mole is 6.02 times 10 to the 23rd, and there are so many atoms in a jar of something, a liquid, a gas, whatever, that quite frankly you can't use just normal numbers, which is why the mole makes things easier. The conditions of temperature and pressure that are 0 degrees Celsius and 1 atm is known as standard temperature and pressure, or STP. This is important. So standard temperature and pressure equals STP, and this equals 1 atm, so 1 atmosphere pressure, 0 degrees Celsius, or 273 degrees Kelvin. And that is the molar volume for a gas. Okay, so whenever anything says it's standard temperature and pressure, it means 1 atmosphere, 0 degrees Celsius. All right. Now, Avogadro showed experimentally that 1 mole of any gas is going to occupy a volume of 22.4 liters. Okay, so it's also 1 mole of gas equals 22.4 liters. Always, you're going to need to know this. Okay, so now if we want to figure out how many moles of gas there is, you can convert. Let's say that we have 3.72 liters at standard temperature and pressure. So let's figure out how many moles there are, and then we can figure out how many particles. All right, so let's say we have 3.72 liters of gas, and we want number of particles. We just convert. All right, so our conversion factor, we have 3.72 liters. We want to go from liters to moles. And so we're going to need to put liters on the bottom and moles on the top, because moles is what we want. So 1 mole equals 22.4 liters. So we convert this, we end up with 0.166 moles. Now we can go from moles to number of particles because of that 6.02 times 10 to the 23rd conversion factor. All right, so we have 0.166 moles. Our conversion factor, we want particles, so 6.02 times 10 to the 23rd over 1 mole, cancels out. You end up with 9.99 times 10 to the 22nd particles. This should be relatively familiar. This is a new conversion factor, but this process we've done before. It's just conversions, that's all it is, okay? So now let's talk about a principle using moles, and let's go through another example, okay? So, all right, calculate the volume that 0.881 moles of gas at standard temperature and pressure will occupy, okay? So we want volume of 0.881 moles at STP. So STP, 1 atmosphere, 0 degrees Celsius, or 273 degrees Kelvin. Okay, so first of all, let's figure out how many liters this is going to be. So we have 0.881 moles times, let's see, we have moles, we want liters, so it'd be 22.4 liters over 1 mole. 0.88 times 22.4 is going to give us 19.7 liters. And that's it. That's it. Okay? So, if we're asked for the volume, then we want liters. if it's a standard temperature and pressure, then the temperature is not changing and the pressure is not changing. So you don't have to worry about those variables at all. All you have to do is convert. You were given moles. You know the conversion is 22.4 liters for every 1 mole. Multiply that conversion factor out. You get your liters. That's all it is. All right? So let's get just a hair more complicated. What happens if they don't give you moles, but they give you mass of gas? Again, this should be relatively familiar. This builds on chapter 10 and 11 and 12, I think. Okay, so, well, I'll leave that for now. Let's take a different problem. Calculate the volume that 2 kilograms of methane gas will occupy at standard temperature and pressure. All right, so our mass equals 2 kilograms. It's methane, so it's CH4. It's at standard temperature and pressure, 0 degrees Celsius. 1 atmosphere pressure, and we want to calculate the volume. We have mass, and we have no way of going from volume to mass. We only have ways from going from moles to volume. Okay, so we need to take mass to moles, so then we can take moles to volume. So, in order to figure out the mass, we need to figure out the atomic mass of methane. So, we add up the masses of each molecule. So 1 carbon is 12, 4 hydrogen are 1 each approximately. And so your molar mass of methane, with the little decimals added in, is going to be 16.05. And calculate that again. Carbon's 12, hydrogen's 1, so 4 of them. All right, so now we have the mass. But our issue is molar mass is in grams per mole, and this is in kilograms. So let's convert. 2 kilograms times, let's see, 1,000 grams in 1 kilogram equals 2,000 grams. Cool, not so bad. Now we know how many grams. We know that there are 2,000 grams, and we know that methane is 16 grams per mole. So how many moles do we have? 2,000 grams times, let's see, 16.05. Oh, I am so sorry. It's 1 mole over 16.05 because we want moles. 16.05 grams, right? So this was our first conversion factor. We first converted from kilograms to grams. Now we're going from grams to moles. 1 mole over the molar mass, which we found up here. So 2,000 divided by 16.05 is going to be 125 moles. So we have 125 moles of gas. We were given 2 kilograms. We took our kilograms to grams. We took our grams to moles. Now we have 125 moles. Now we can go from moles to volume. So we have 125 moles times. Our conversion is 22.4 liters over 1 mole. 125 times 22.4 is 2,800 liters. And that's what it is. So those are the last problems in your Juno pod. Okay? If you need another example, then I will, a little bit later, I will make another example of me walking through, but I'd also be happy to video chat you. And of course, we do have our group video chat on Wednesday at 10 if you need any more help with this. Okay? It's just conversions. That's all it is. Don't let it freak you out. You've got this. Okay? Just think through what I have. Where do I need to go? How do I get there? All right? So, good stuff, you guys. Good luck with your Juno pad, and I will talk to you later. Bye.